Okay, great. So it's a pleasure to have Simon Riche today from Université Clermont Auvergne. He will tell us about towards a modular to realizations equivalence.
Thank you very much. I'd like to thank Maki and Jordi for the opportunity to speak. And I've been watching most of the talks of this seminar, but it's the first time I can participate live. So I'm happy to do so today. So I'm going to explain some joint project with Roman Bezukavnikov, which was originally also joined with Laura Ryder, and our goal is to provide some positive characteristic version of the two realizations equivalence that was discussed in previous talks of this seminar. So recall that we have this affine Hecke algebra, which has two geometric realizations. One is in terms of perverse sheaves on the affine flag variety of the given reductive group. And another one is in terms of coherent sheaves on the Steinbeck variety of the Langlands dual group. And our goal is to obtain an equivalence of monoidal triangulate categories, which relates these two words. And so in the case of characteristic 0, this is already known. This is a result of Roman Bezukavnikov. And now we are interested in the case when the coefficients are a field of positive characteristic. And we have various motivations to do so. Some of these motivations come from the geometric Langlands program. And well, I'm not going to say much about that because I don't know exactly how it works, but people in geometric Langlands seems to to have applications in mind for such an equivalence. And my personal interest comes from representation theory of reductive groups and the algebras of a field of positive characteristic. And in fact, in the recent years, due to various people, we now have some geometric relations. Some geometric realizations of some categories of representations of reductive groups or of the Lie algebras in terms of things which are closely connected with perverse sheaves on the affine flag variety or coherent sheaves on the Steinbeck variety. And by relating these two worlds, we hope to get new tools for this geometric study of representations of reductive groups. And one more direct application, direct application of this construction that we have in mind is to a proof of the Finkelberg-Mekovich conjecture, and I'll say a few words about that at the end of the talk. So I'll start by recalling what the players of this story are. So I will have a G reductive algebraic group over a field F, which is algebraically closed of characteristic P. So this F will be the field of definition for the varieties on the constructible side. So it's not the same as the coefficients. The coefficients will come later, but for some technical reasons, I want to work over a field also, well, with some varieties defined over an algebraically closed field of positive characteristic. And so I will not be very precise about the technical assumptions, but usually it's safer to assume that the group has connected center. And I want to choose a maximal torus T and a Borel subgroup B. And out of this data, I can define the loop group LG, which is a group in scheme over F. I have the positive loop group L plus G, which is a group scheme, but not of finite type. And finally, I have the Iwahori subgroup I, which is the preimage of the Breuer subgroup under the morphism of evaluating z at 0. So this is a subgroup scheme in L plus G. And I will be interested in essentially in two different varieties. First, the Affine-Grassmannian, which is the quotient of Lg by L plus G, and the affine flag variety, which is the quotient of Lg by the Iwahori subgroup. So as you know, the affine flag variety is some kind of infinite dimensional analog of the flag variety G mod B, and the Affine-Grassmannian is some kind of infinite dimensional version of a parabolic flag variety G mod P for some parabolic P. And one category which is not the category that we want to understand here, but which will play a major role in the story, is the Sataki category. So for this, I choose a field of coefficients K, which will be, well, it can be either a finite, so it will be either some finite extension of QL or some finite field of characteristic L, which is different from P. And for some technical reasons, sometimes we want L to avoid some small values for L. And okay, so it can be either a finite field or a finite extension of QL or some algebraic closure of these. And in all of this context, we have a definition for the category of L plus G equivalent K-perverse sheaves on the Affine-Grassmannian in the sense of étale perverse sheaves. So this is a very nice abelian category, and an important structure that we have on this category is the convolution product. So the L plus G equivalent product. So recall that this convolution product is naturally defined on the L plus G equivalent Dirac category, but it turns out, and this is a very important property of the Affine-Grassmannian, that in fact this convolution product is T-exact. So it sends, so when you convolve two perverse sheaves, you again get a perverse sheaf. And so this monoidal structure descends to, well, induces a modular structure on the Sataki category, on the category of perverse sheaves. So this is the classical part of the story. And what we want to consider now is some analog for the affine flag variety. So now I want to consider the I equivalent Dirac category of sheaves on the affine flag variety. And I will have a notation for this. This will be the DII. And again, for the same reason as for sheaves on the Affine-Grassmannian, we have a monoidal product. This time the I equivalent product. It is so again. This is a product on the Dirac category, and this time in the Dirac category we have of course the subcategory of perverse sheaves. But this time, the monoidal product will not be T-exact. The category of perverse sheaves is not stable under the convolution product, and this is some difficulty that we have here that we really have to work with. Well, we really have to work with triangulated categories, and well, we will try to get back to the world of abelian categories, but this will require, well, this will involve some work and some tricks. So there is a relation between these two worlds, the world of constructible sheaves on the Affine-Grassmannian and on the affine flag variety, and this is provided by Categori's central functor. So this functor is a functor from the Sataki category, so the category of L plus G equivalent perverse sheaves on the affine flag on the Affine-Grassmannian to the Iwahara equivalent Giraffe category of the affine flag variety. So I will not recall the definition, but well, we have seen this in some previous talks. In the construction, one considers a certain scheme over A1, and the scheme has the property that the fiber over the generic fiber is isomorphic to the affine Grossmanian, while the special fiber is isomorphic to the affine flag variety. And so we have a nearby cycles functor, which can be used for this with this scheme, and it provides a functor from the category of perverse sheaves on the affine Grassmannian to the Giraffe category of sheaves on the affine flag variety. And well, in fact, this functor is T exact. But if we want to make sense of one of its properties, which is the fact that it is monoidal, then well, we have to make sure this functor takes values in the monoidal category. So we want this category to take values in the Giraffe category. But in fact, the image of any perverse sheaf will be a perverse sheaf. So we have a number of structures on this functor. First, we have a canonical automorphism given by the monodromy. I will come back to this in a moment. But so we have this automorphism, and the other thing that we have is that Z is a central functor. So there is a formal definition of what it means to be a central functor, but I will not. Well, it's just a list of axioms. But well, a list of structures and some axioms that they should satisfy. So one of these structures is that we have a monoidal structure on this functor, plus for any F perverse sheaf on the affine Grassmannian and G complex on the affine flag variety, we have a canonical commutation isomorphism between Z of F and G. So this is so we have some canonical bifunctorial isomorphism like that, and we have a list of compatibilities between these two structures, which ensure that what we get is what is called the central functor. So this is what we have on the constructible side, and so the other side of the story is the coherent side. So this coherent side will be related to the Lagrange dual group of a K. So we have I have my field K. I have the Lagrange dual group G check of a K, and in fact I have a canonical choice for this. The Lagrange dual group is defined up to isomorphism, but in this, but since I have the geometric Sataki equivalence, in fact it provides me with some canonical group scheme, giving me this Lagrange dual group. So the category of L plus G equivalent perverse sheaves on the affine Grassmannian is is equivalent as a monoidal category to the representations of the dual group. And I will just so I will mainly not work with the functor Z that I just defined, but its composition with the geometric Sataki equivalence. So I introduce the notation of this notation curly Z for the composition of Gates-Grüss functor with the geometric Sataki equivalence. Okay, so I have this group G check over K, and inside this group I have a Borel subgroup B check over K and a maximal torus T check over K, and I will denote by U check over K the unipotent radical of the Borel subgroup. And also have a notation for the Lie algebra, this German G. And to this data, with this data, I can define the Schwenger resolution, which is the a vector bundle over the flag variety of G check, and it is the vector bundle associated with the action of the Borel subgroup B check on the Lie algebra of the unipotent radical. And I have the slightly larger Grotnik resolution, where instead of taking the Lie of the unipotent part, I take the Lie of the whole Borel subgroup. So this is also a vector bundle over the flag variety. And using these varieties, I can define various versions of the Steinberg variety. The most useful version is the one that I will denote by ST, which is the fiber product of the Grotnik resolution of two copies. It's a fiber product of two copies of the Grotnik resolution over the Lie algebra. So this is one version of the Steinberg variety, but I can play the same game with the Schwenger resolution instead of the Grotnik resolution, and I can also mix these two things and consider a version of with on one side the Schwenger resolution and on the other side the Grotnik resolution, and all of these varieties can be called the Steinberg variety, and in fact the three variants. Well, some version of these three variants will show up in what I'm going to say next. So I have these varieties, and so my main object of interest is the derived category of G-check equivalent coherent sheaves on the Steinberg variety ST, and so I can play the same game with the other versions, and in so on this variety I have some monoidal product, which is constructed using the usual setting for convolution. So I consider some variety cooked up out of three copies of the Grotnik resolution. I can project on the first two components, on the last two components, or on the first and the third. And using this diagram, I get some monoidal product. Well, so this works very well with this works for this version of the Steinberg variety. For the other versions, it's a bit more subtle, but I will not comment on these difficulties. And so just to conclude this part, we have this constructible side where I have this monoidal category DII. I have the coherent side where I have this category of coherent sheaves on the Steinberg variety, and I want to get some relation between them. So I will start by commenting, to make a few comments related to what has already been discussed in the seminar about the characteristic zero setting. So we have two main new difficulties when we try to pass from the characteristic zero setting to the characteristic P setting. So one is something very classical, that the classical difference between representations of reductive groups or fields of positive characteristic compared to fields of characteristic zero is that the category of representations is no longer semisimple for positive characteristic coefficients. And so usually the way we deal with this difficulty is by working with tilting objects in terms instead of any representation. So recall that in terms of the geometric Sataki equivalence, tilting representations correspond to parity complexes on the affine Grassmannian. So in a number of statements, we will have to relate to replace an arbitrary representation by a tilting representation, and this usually suffices to deal with this problem. Also, although this might sometimes involve some additional technical difficulties. And the second main difference between the characteristic zero setting and the characteristic P setting has to do with the monodromy automorphism on Getz-Gröss functor. So nearby cycles construction makes sense for any coefficients, and so in particular it makes sense over fields of positive characteristic. And in any setting, we always have a monodromy automorphism, but usually in the characteristic 0 setting, one takes the, well, at least in the setting that we are interested in, this monodromy automorphism is unipotent. And so we take the logarithm of this unipotent automorphism, and we get some nilpotent endomorphism. So over fields of positive characteristic, of course, taking the logarithm is more problematic, and usually it's not defined. So we'll not be able to do so, and so we will really have to work with the monodromy automorphism and not its logarithm. And on the geometric side, this means that instead of working with the additive versions of the Schwenger resolution, Grothendieck resolution, and Steinbeck variety, it's usually better to work with some multiplicative variants. So I will use the notation Schwenger M for multiplicative for the variety defined as for the Schwenger resolution. But now I take the unipotent resolution, the unipotent radical of the Borel subgroup, and not its Liège. And so, as before, the action of the Borel subgroup is by conjugation. I also have a multiplicative variant of the Grothendieck resolution where I take the Borel subgroup instead of its Liège, and then I can play the same game as before and get a multiplicative variant of the Steinberg variety. Okay, so that's about the difficulties, well, the differences between characteristic P setting and the characteristic 0 setting. I also wanted to say a few words about the three possible variants of the equivalence. So this was already there in the characteristic 0 setting, but I don't think it was mentioned in, well, at least not really. At least it was not really emphasized in the talks. But we in fact expect to get three variants of the equivalence. So first we want to, well, we can consider the derived category of, well, so just this category dii of I equivalent complexes on the affine flag variety, and we expect these to be related to sheaves to coherent sheaves on the version of the Steinbeck variety involving the Schwenger resolution. So I did not mention the equivariance here, but that's it should be there. There is a difficulty in this version that in this version we really have to take some derived fiber product. When we take the derived fiber product here, we really get something which is actually derived, and so if we want to work with this this version, when one has to work with some DG schemes and consider some DG coherent sheaves on this DG scheme, and this creates some technical difficulties. And another drawback of this version of the equivalent is that in the category of Iwahori equivalent perverse sheaf, we don't have any good notion of tilting perverse sheaves, and so this is also something that is crucial in the various approaches to these constructions, and so it's difficult to work directly with this version. So one way to remedy this drawback is by replacing this Iwahori equivalence, so this first I, by equivalence against the pro-nipotent radical of the Iwahori subgroup, so this IU. Well, so in concrete terms, it's just the preimage of the unipotent radical of B under the evaluation of Z at 0. And so if we replace I equivariance by IU equivariance, one gets a triangulated category DIUI. And this version of this category should be related to derived category of coherent sheaves on an actual scheme, which is the fiber product of one copy of the Grothendieck resolution with one copy of the Schwenger resolution. So this is this non-symmetric Steinberg, this non-symmetric version of the Steinberg variety. What is nice about this version of the equivalence is that that we no longer have to work with DG schemes. In fact, if we take the derived fiber product here, we just get some scheme. There is no derived structure here, so we have a nicer scheme, and we have solved the difficulty of the absence of tilting perverse sheaves in this world of IU equivalent perverse sheaves on the affine Planck variety. We do have tilting perverse sheaves, and we can work with them. But what we have lost in this process is the symmetry between the two sides. On one side we have this IU, and the other side we have I, and for this reason there will be no modular structure on this category. In fact, on either side of this equivalence. And that's another thing that's important for the construction. So in fact, what we will use is a third version of the equivalence, which also involves some technical difficulties, but which in the end turns out to be the most suitable version for this construction. So for that, we consider the in-scheme FL twiddle, which is the quotient of the loop group by this IU. And so this is a T-torsor over the affine Planck variety, and I will denote by pi the product, by pi the quotient map. So this is some kind of analog of G mod U of the basic affine space. And I can define the category DIUIU, but so for that I take so I want to consider IU equivalent IU equivalent complexes on FL twiddle, but I don't want to. Well, this category is too big for our purposes. I want only to consider the subcategory generated as a triangulated category by objects, objects coming from the category DII. So generated by objects of the form pi upper star f with f in my category DII. And so this again in this setting I have a monoidal product. So this IU equivalent convolution, which is a monoidal product on this category. Well, first on the IU equivalent derived category, and it stabilizes the subcategory DIUIU. There is one slight subtlety that there is no there is no unit object in this category, but I'll come back to this in a minute. But so I have this category DIUIU, and I have a subcategory of perverse sheaves PIUIU. So this is better because we have recovered some symmetry, but this category of perverse sheaves is not highest weight anymore. The problem comes from the fact that the torus has a non-trivial cohomology, and that's bad. But there is a way to fix this, and this is where so this can be fixed using a construction due to Zhou Weiyun. And Zhou Weiyun has explained how to construct some kind of completion of the category DIUIU, which will be denoted DIUIU hat. And so I will not explain precisely the definition, but it is a certain subcategory of the category of pro objects in this category DIUIU. So we want to consider some pro objects. So we want to consider some additional objects. So to add, in a sense, to add objects in this category. but if we consider all pro-objects, this is not good enough because the category of pro-object in a triangulated category is not triangulated. Is not triangulated. So we want to add, but it's very important for us to work with triangulated categories. So it is a bit subtle to understand how how to define some subcategory of this category of pro-objects which is triangulated. But Yun has done that for us, and so we have this completion of the category, which is the triangulated category we will work with. And by passing the monoidal product on the category DIU induces a monoidal product on this completion. And also Zhou Yun has explained how to define the T structure, perverse T structure on this category. So we have a category of perverse sheaves. And this is the category we will work with. And so we can now expect to have an equivalence between this completed category and some category of equivalent coherent sheaves on some completion of the Steinberg variety. So this hat here is some completion. I will explain this a bit more at the end of the talk. But so this category DIU hat contains as a full triangulated subcategory the category DIU, and this subcategory should correspond to coherent sheaves on the multiplicative version of Steinberg variety, which are supported on the preimage of the unipotent cone. So this is this U here in the notation. And so with this version, we have added some technical difficulties with on the constructible category, and well, this makes some of the construction a bit more difficult. But we still have some good theory of tilting perverse sheaves, and we do have a convolution product. And so this is really this version here that we will work with, and in the characteristic 0 setting, this is a fact that we can recover the other versions from this version. And in the characteristic P setting, this should work the same. And so our aim will be to construct an equivalence of this form. So Maki, am I supposed to have a break at some point, or?
Yeah, we should have a break. I know you have one more page before this is part 2, but is it okay to take a break here for a few minutes?
Yes.
Okay.
Definitely.
Okay. So yeah, let's be back at 7:43.
Good.
Hi Simon.
Salut.
En fait, je me suis pas trompé du jour et après ton message, j'ai pensé à c'est forcément demain.
Mais c'est compliqué parce que demain, selon quand on le dit, demain, c'est pas toujours le même moment. Donc,
Oui, exactement. Oui.
selon quand on le dit et l'endroit du monde où on le dit, c'est pas forcément le même moment. Bon, mais t'es pas arrivé très en retard encore.
J'ai manqué 6 minutes, je pense. Jusqu'à maintenant, j'ai compris.
Bien. Bon.
Okay. 7:43. You can start the second part of the talk.
Okay, so I'll continue. So the first thing one can try if one wants to get some characteristic P version of this equivalence is try to copy the characteristic 0 proof that we already have. And well, this is the first thing I tried, but in fact, and if one tries to do that, one runs into some technical difficulty, which seems not so serious, but which I was not able to fix. And so I'll try to explain that. And if anyone is interested in discussing this, I'll be happy to explain a bit more about that. But recall that the first step of the characteristic 0 version was to prove this Arkhipov-Bezukhalnikov equivalence, which is a version which involves only the geometry of the Schwenger resolution. There's no Steinberg variety in here. And the way that Arkhipov and Bezukhalnikov construct their equivalence is by constructing some factor from coherent sheaves to constructible sheaves, and they construct this functor by reconstructing the geometry out of the structure that we have on the constructible side. So if one tries to, well, so one can try to copy this construction, and at first this works very well, with the only subtlety that one has to work with the monodromy instead of its logarithm. So this replaces the Lie algebra by the group. But so we have this affine completion of the basic affine space X. So this is an affine singular variety. And one can cook up some closed subscheme in the product with the group, which is denoted by Y, which is defined in a very simple way. It's just the closed subscheme defined by an ideal generated by the image of a certain map from functions on X to functions on the product, which is given by this simple recipe. So we have this co-multiplication delta of F, which comes from the action of G on X, G check on X, and we have this difference, and this defines some closed subscheme Y, and this closed subscheme contains not exactly the multiplicative version of the Schwenger resolution, but rather some torsor over this, which is obtained by inducing the U check to G check. I mean, okay, this twisted product, which is a torsor over the multiplicative Schwenger resolution with fibers certain torus. Well, so the dual torus. So the Schwenger resolution is the quotient by a free action of a torus. And so this is just copying the Arkhipov-Bezukhalnikov construction. And in fact, when one replaces the group, well, the Lie algebra by the group, it is well known that the Schwenger resolution is in fact unchanged. It's an isomorphic variety, and this torsor over it will mean it will also have a version for the Lie algebra, which is again isomorphic. But the subtlety is that this Y has a version for the group and one a version for the Liège, but these two versions are not isomorphic. These even though the open parts are the same, if you complete it to an affine scheme, this affine scheme Y, you will get different schemes for the group and for the Liège. And as in the Archipoff-Vesselnikov construction, we have a functor of restriction to the open part from a certain category of coherent sheaves. So this free means this is the full subcategory consisting of so free coherent sheaves, things that form V tensor the structure sheaf. And so we can restrict to the open parts and get a functor from this category to the derived category of G check times T check equivalent coherent sheaves on this torser, and which is the same as the derived category of coherent sheaves on the multiplicative Schwenger resolution. And the same construction as in the Archipoff-Vesselnikov functor provides a functor from this category here of coherent sheaves on Y to the derived category of I equivalent perverse sheaves on the affine flag variety. And here is where the difficulty comes, that in the characteristic zero version, Archipoff-Vesselnikov have a way of describing the derived category of coherent sheaves on the Schwenger resolution as a Verdier quotient of this category of coherent sheaves on Y. And while it turns out that replacing the Liège with the group introduces some technical difficulties, and I was unable to generalize their results, and so to describe this functor as a Verdier quotient. So I will not say much more about this here, but if someone is interested, I'll be happy to explain this difficulty in more detail. And so this is as far as I can go, and I cannot go further in this construction, and in particular, I cannot copy the characteristic zero version of the equivalence. So we will use some different tools, and in order to explain these tools, I want to explain what happens in some toy example, which is the example some similar setting when we work with finite flag varieties instead of affine flag varieties. So the ideas of this come from a paper of Vesselnikov with Beilinson and Mekovich. And so in this setting, we work with sheaves on G mod B, and we look at the U equivalent derived category of sheaves on G mod B. So I will denote this by DUB. And it's well known that this category is equivalent to the derived category of perverse sheaves, and also to the homotopy category of the category of tilting perverse sheaves. And so if we want to describe this triangular category, it's enough to consider to describe tilting perverse sheaves. And this is where Zergel theory comes in the picture. So we have tilting perverse sheaves inside the category of perverse sheaves, and Zergel explained that we, in order to describe this category, we should study a certain functor V, which is taking hom from the projective cover of the skyscraper perverse sheaf, skyscraper at the unit orbit. And it provides us with a module over endomorphisms of this projective object. And what Beilinson, Vesselnikov, and Mekovich explained is that, in fact, this functor V is nothing else than the quotient functor to a certain Serre quotient, the Serre quotient of the category of perverse sheaves by the Serre subcategory generated by all simple objects whose label is not the unit element. So in fact, taking this functor hom from the projective cover is exactly the same as taking this quotient functor. Okay, so this is important for us because in in the setting of the affine flag variety, the category of perverse sheaves will no longer have enough projective objects. It's possible to produce some projective objects, but this involves some. We have to work with some pro objects, so it creates a lot of technical difficulties. Whereas this quotient by a cell subcategory, this is something which which is very easy to adapt to the affine setting. And if we want to go further and try to explain the relation with coherent, some category of coherent sheaves on some schemes related to the dual group, in fact, it turns out that the endomorphism algebra of this PE is a commutative algebra, and it is the functions on the fiber product of the torus with the unit points over the adjoint quotient, so the quotient of T check by W. So in characteristic 0, this is one known result of Zögel, and in the positive characteristic setting, we generalized this in a recent paper. Well, in a paper from a few years ago with Bezukalnikov. So we have this quotient functor, and in fact, so this is for the U equivalent setting, but one can play exactly the same game for the B equivalent setting. So for B equivalent perverse sheaves, and in this case, one can check that the quotient that we get is just equivalent to vector spaces. And one can also play a similar game for U equivalent perverse sheaves on G mod U. And again, we take something, we only consider the perverse sheaves coming from G mod B. And in this case, the category of the quotient category that we get turns out to be equivalent to coherent sheaves on the fiber product of two copies of the torus over the quotient by the Val group, and this 0 here means coherent sheaves supported set theoretically at the unit point at the point 1, 1. And so this is some kind of geometry that starts to look like what happens for the Steinberg variety, and this is something that we'll see again later. Okay, so I think I can finally start presenting the results that we have on this construction. So our plan is to.
Can I just ask quickly on your previous slide? So there was a question in the chat, but I assume iPad is Roman, and he answered it.
Yeah, so this is just the usual quotient of an affine scheme by an action of a finite group. So this functions on the the spectrum of W invariant functions on the torus.
And also, when you say if L is not too small, that quotient is equivalent to vector spaces. Do you mean that's what you can prove, or you actually know that it's not that for small L?
This is what I can prove. I would suspect that it's not true. Yes. Well, this is definitely true in very good characteristic. I don't know, because so there is something that I did not really explain. So in fact, this category PBB depends on the category of U equivalent perverse sheaves. It's unchanged if you replace a group by some isotopic group, but this BB version does change when you change the isotopy. So I think it. Oh, okay, so I don't remember exactly, but maybe it's always true for adjoint groups. But for simply connected version, you need L to be very good or something like that. Okay, so our plan to construct this this equivalence is to proceed in 3 steps. So there is one step which is already written and has been posted on the archive last year. there is a second step that we are working on at the moment, and which hopefully will appear in the month to come. And then there is a third step, which is just as a for which nothing is written at this point. But so I'll start by explaining the first step. And so one way to understand the construction that we consider is to get back to a billion. Is that we want to get back to a billion categories. And so we one of the difficulties is that on the affine flag variety, the convolution product is not the exact, so we definitely have to consider some truncated category. But there is a way to reconstruct some abelian modular category in this setting also. So for that, and this procedure is related to what I just explained about the finite flag variety. So so recall that the Iwahori orbit on the affine flag variety are parameterized by the extended affine Weyl group, which is the semi-direct product of the finite Weyl group by the co-weight lattice. So this extended affine Weyl group is essentially a constant group with the length function given by the dimension of this strata. And so the simple objects in the category PII, they are in natural bijection with this strata, so with the extended affine Weyl group. So for any W, I have some perverse sheaves, some perverse sheaf ICW, and I can consider the Say subcategory of PII, which is denoted by PII plus, which is generated by the simple object associated with elements of positive length. So this is a Say subcategory, and then I can consider the quotient of PII by this Say subcategory, and I get the category that I will denote PII0, and I will call the equivariant regular quotient. So in terms of simple objects, we have killed most of the simple objects in this quotient, but as we know from characteristic zero, from Zeugel theory, killing a lot of simple objects can still be it doesn't kill all the information about the category. We might still have very interesting things in this quotient, and in particular if we want to understand things related to tilting perverse sheaves. So I will denote by pi I0 the quotient functor, and as I mentioned previously, this will allow us to get some monoidal abelian category because of the following lemma, which is really not difficult to check. So if I have two perverse sheaves on the two I equivalent perverse sheaves on the affine flag variety, I can convolve them. Then I can take the zeros perverse cohomology of this object, and then I can project to the quotient. So this gives me some bifunctor from PII times PII to PII0. So first of all, this bifunctor factors through a bifunctor from PII0 times PII0 to PII0, and this gives me some modular product on this category. So this defines a modular structure on the abelian category PII0. And this modular product turns out to be exact on both sides. So in this way, out of highly not T-exact modular product on a truncated category, we cooked up some exact with some modular structure on some abelian category, but which is not just perverse sheaves, it's a quotient of the category of perverse sheaves. And yes, and the reason why we get a monoidal product on this is essentially because in this quotient category, the only simple objects are the classes of simple pervasives corresponding to orbits of dimension 0. So orbits corresponding to points. And if you convolve two things of this form, of course you get a pervasive, and this is essentially the reason why you get some modular structure here. So this is for the constructible side, and on the coherent side, we choose some regular unipotent elements U in the dual group, and we'll denote by Z of U its centralizer in the check, and with some appropriate restrictions on L, this is a smooth group scheme, so there is no question about the structure we want to consider on this centralizer. And so the main result of the first paper that we wrote on this project, which is joint with Roman Bezganikov and Laura Ryder, is that, again, with some restrictions on L, there exists an equivalence of billion modular categories between this category, this equivalent regular quotient, PII0, and the category of representations of the centralizer of U. And this equivalence is compatible with geometric Sataki equivalence in a sense. So in the following sense, we have this geometric Sataki equivalence, which relates pervasives on the affine flag variety and representations of the dual group. On the constructible side, we can consider the functor of applying a Getz-Gruss functor and then projecting to the quotient, and so we get a functor to PII0. And on the coherent side, we can consider the functor of restriction from representations of the group to representations of the universal to the centralizer of U, and these two functors are related by this commutative diagram. So this is not the correct Z. So there is this one should be this Z. And so I explained that, well, so one way to justify this construction comes from the case of the finite flag variety. And so in fact, the finite flag variety is, well, you can see the finite flag variety in the affine flag variety. And so the quotients that we considered on the finite flag variety, you can see it as a full subcategory in this category PII0, and so I explained that the quotient for the finite flag variety is just vector spaces. The quotient for the affine flag variety is representations of the centralizer of the unipotent elements, and via these identifications, the functor is just sends a vector space to itself with the trivial representation. Okay, I still have a lot of slides, so I might take more time than what I was given officially. Well, is it a problem or?
I'm okay with this, but well, so yeah, maybe, I mean, I guess maybe we can take a little break. How much longer do you think you will need?
I can try to finish in 30 more minutes. Is it if? Well, I can stop. I mean.
Also, no one's forced to stay.
Yes, I will not be offended if you are tired and want to stop there.
So I'm very happy to continue. Yeah, maybe we can just say anybody's free to leave, and of course the recording will be available. But yeah, I'm happy to continue.
Okay, so should we have a break now or no break? I don't know.
Sure, let's take just a few minute break again. We can start, say 5 minutes again, so 8:12.
Good.
Okay, great. Are you there, Simon?
Yeah, so I am there.
Yeah. Okay, great. Let's start the last part.
Okay, thank you. Yes, so I should have mentioned that this this theorem also in the characteristic zero setting, this some form of this theorem in fact also appears in the paper of Arkhipov and Bezganikov. And so the strategy that we use is to in fact well, start take this this statement as the first step towards the construction of the equivalence. So the main tool to prove this theorem is the following proposition, which appears in some older paper of Bezganikov, which is so this is a very general statement which has to do with Tanakian formalism, and whose proof is not very difficult. So we consider some algebraically closed field K and some affine K group scheme of finite type G, and also some K-linear abelian category A with a modular structure which is exact on both sides. And well, there are some technical conditions that one needs to add, but that's not really relevant for what I'm going to say. And we assume that we are given an exact central functor f from representations of G to A, such that any object in this category A is isomorphic to a subquotient of an object in the image of this functor. And well, so this is what we have. And then given such a central functor, there automatically exists a subgroup scheme H of G and an equivalence of categories between A and representations of this subgroup scheme, such that F corresponds under this equivalence to the restriction functor. So this this proposition turns out to be extremely useful in this context, and one important property of one important remark about this statement compared to some other statements of this kind in the Tanakian formalism is that in this setting we start with this category A, but we usually in Tanakian formalism we start with some modular category plus a fiber functor, but here we have just the modular category and we don't start with a fiber functor, but instead we start with a functor from representations of something. And also we do not need to have a commutatively constraint on the category A at the start. Well, in fact, in the proof we do construct some fiber functor, and in the end, if we have an equivalence like that, the category will turn out to have some commutatively constraints, but we do not have to have these things at the start. What we only need to get is some central functor from a category of representations of a group. And this is exactly what we have in this setting because of Category's functor. So we have this functor, this category PII0, and we have a functor from representations of the dual group, which is given by applying Category's functor and then projecting to the quotient. So this is fine. This is the central functor that we needed. But there is a slight difficulty that we had this technical requirement that any object is a subquotient of something in the image, and in this setting it's not clear at first that it is true. So we consider, but this can be easily fixed by just replacing this category P0 by some twiddle version, which is the abelian subcategory whose objects are subquotients of things in the image. So we just force this condition to be satisfied, and then we are exactly in the setting of this proposition. So this category PII0 twiddle will be equivalent to representations of some subgroup H of the dual group. And also we have some other structure on the central functor, on Getz-Lewis functor, which is the monodromy. And so this is an automorphism of the functor Z, but it also, of course, provides an automorphism of the composition with pi 0. And once we have the equivalence between this category with representations of H, we can forget the H action. It provides us with a functor 2 vector spaces. And the monodromy on Getz-Lewis functor provides an automorphism of this composition, which is just the forgettable functor from representations of the dual group to vector spaces. And Tanaka formalism tells us that the data of an automorphism of this functor is equivalent to giving an element in the group. And because all of this is, well, because this comes from an automorphism of Z, this will tell us that the subgroup H will be contained in the centralizer of V. And in fact, so this is the starting point of the construction, and the main work required to prove the theorem is to prove first that U is unipotent regular. So the fact that it is unipotent is essentially the same as saying that the monodromy on Getz-Lewis functor is unipotent, which is something well known. But the fact that it is regular is more complicated. Then we'll prove that H is in fact the whole of the whole centralizer. Here, this inclusion is inequality. And finally, there is a last thing that we need to check, which is that this twiddled version is in fact the whole category P0. And the main tools in order to prove this property come from tools which were already there in the Arkhipov-Vesganikov paper. So first, the fact that central sheaves admit Wakimoto filtration. So this is proved by Arkhipov-Vesganikov, and in fact, the proof applies directly to arbitrary coefficients. So central sheaves always have Wakimoto filtrations by Wakimoto sheaves. And another important property is the following. So I had this my Iwahori subgroup, which was initially defined in terms of a negative subgroup, a Borel subgroup corresponding to negative roots. But I can consider the opposite Iwahori subgroup, the one defined in terms of the positive Borel subgroup. And I can consider a morphism to the additive group defined by, so this by definition is the preimage in the positive loop group of U plus. So it has a morphism to U plus. And then I can consider a morphism from U plus to the additive group, which is non-trivial on any simple root subgroups, and which is 0 on any root subgroup corresponding to a non-simple root. And the composition will be denoted by chi. And well, so this is the same construction that appears in this story about the Iwahori-Whittaker model of the affine flag variety of the affine Grossmanian. One can play the same game on the affine flag variety and consider the category of perverse sheaves which are equivalent against the pullback of the Artin Schreier sheaf. And one gets a very nice category of perverse sheaves on the affine flag variety. And this category is useful here because so we have an averaging functor from the category of Iwahori equivalent perverse sheaves to this Iwahori-Whittaker category. And what we prove in this paper, which so in the characteristic 0 setting was in the Arkhipov-Vesganikov paper, but the characteristic P version, the positive characteristic version requires more work, is that if we start with a tilting representation of the dual group and consider the corresponding central sheaf Z of V, and then of average, then what we get is a tilting perverse sheaf. So these central perverse sheaves, they are very nice, but The structure in the category of pervasive is not really well understood, but if we average against this Ewar-Whittaker character, we get some tilting pervasive. And in fact, this is the main, this proposition is the main reason why we have some technical conditions on the characteristic in the statement previously, because the proof is the proof uses so essentially the same procedure as in paper of Akimov-Vesganikov, which is a reduction to the case of minuscule and quasi-minuscule highest weights. And in the case of tilting representations in positive characteristic, this technique was already used crucially in the paper of Juteau, Martin, and Williamson. And this works well under some assumptions, under some appropriate assumptions on the characteristic. And so we have the same restrictions as in this paper of Juteau, Martin, and Williamson because of this reason. And in fact, so using this, it suffices to prove this proposition in the case when V has minuscule or quasi-minuscule highest weight, and the case of minuscule highest weight is easy. There is, and this is the same proof as in characteristic 0, and it's really short. The case of quasi-minuscule highest weight is, on the other hand, is surprisingly difficult. Well, surprisingly to me, and one needs to work quite a lot to treat the case of quasi-minuscule highest weights. And in fact, in this, and a crucial ingredient in the proof of the quasi-minuscule highest weight case is the fact that V is regular. So we need to prove that V is regular before proving this proposition, because this is used crucially. And the reason why this proposition, this property is relevant in the proof of our theorem is that, in fact, this Ewar-Whittaker category, it's also equivalent to some quotient of the category PII. So this is not obvious, but this is something that was already present in this Akimov-Vesganikov paper, and which we generalize also to the modular setting. Okay, so this is what is in the paper with Laurent Ryder. So it turns out that to proceed to the second step of our construction, one needs one needs to understand the construction of this equivalence a bit better and a bit more concretely, and this is what I'm going to explain now. So this is based on a lemma that was already discussed in the talk about the Akimov-Vesganikov construction, which is the place where the geometry of the Lie algebra was entering the picture in this construction, and it is based on the following easy and general lemma. So we consider as before, K is an algebraic closed field of positive characteristic, G is an affine K group scheme of finite type, and C is a K-linear monoidal category. And we assume we are given a monoidal functor from rep G to C. And the question is, and we assume that we have some monoidal functor plus some automorphism of the functor, which has an appropriate compatibility with tensor product. Then what this lemma tells you is that automatically your functor extends to free coherent sheaves on the adjoint, on G for the adjoint action. So this means that the objects in free coherent sheaves are just in bijection with representation. So on the objects you don't do anything, but there are more morphisms in this category, and the extension of the action of the functor to these extra morphisms is in fact entirely determined by this automorphism that we have, and corresponds to some tautological. The automorphism NV is the image of some tautological automorphism that we have on this tensor product. So in the characteristic 0 setting, the version that was there was for the Lie algebra. So the condition on the automorphism. Well, so in this case we don't have an automorphism but some endomorphism, and the compatibility with tensor products is a bit different. Well, it's slightly different, but this is the version for the group. This works exactly the same. So we can use this lemma to extend Gates-Greaves functor to these free coherent sheaves. And in particular, we look at the case of the Gates-Greaves functor applied to the regular representation. So the functions on the group, O of G check for the left action. And we look at morphisms from the structure from the structure sheaf in G check to the tensor product O of G check tensor O G check. So this is a free coherent sheaf, and it's not difficult. Well, so these morphisms identify with G check equivalent functions on 2 copies of G check for the appropriate action, and what we get is just functions on the group. And so this means that we have a morphism, an algebra morphism from functions on the group to morphisms from the skyscraper sheaf to the central sheaf associated with the regular representation. And in this way, we get an action of functions on the group on this central sheaf, because, well, if we have a morphism like that, it's not difficult to cook up some action on this central sheaf. And so we have this central sheaf, and we can tensor over tensor over functions on the group with functions on the element U. And in this case, in this way we get an ind object R. So R, which is an ind object in the category PII, which, and from the fact that we have a yes, so yeah, O of G check is an algebra. So when we apply the central functor, we get an algebra object in DII, and it turns out that this tensor product still is compatible with the product in an appropriate sense. So R is an algebra object in this category of ind object in PII. And from the co-multiplication on functions on G-check, one gets some kind of structure of module for this R. So one gets some morphism from R to the tensor product with functions on the centralizer of U. And in fact, in terms of this data, one can describe explicitly the functor providing the equivalence from the other from the theorem. We just take harms from the skyscraper, the image of the skyscraper sheaf in the quotient to the image of this algebra in the quotient convolved with F. So this is one way to reconstruct a posteriori the functor given the equivalence, and this will be important for the third step, for the second step of the construction, as I will explain now.
Sorry, can I actually
Yes,
ask you about the previous slide? So this the action of O of G hat on Z of O of G hat. So is that not the same as the one which comes from viewing O of G hat as a bimodule for O of G hat in the category of representations? Or I mean,
I don't think so. I mean, the O of G check is not, well, it's of course a module over itself, but this is not compatible with the action of the group. so you need to twist this in a way to make it compatible with the action of the group, and this is, I mean, this is not compatible in the group in the sense that you also have to take into account the action of the group on.
Okay, so I thought I mean there is a like a left and a right, and so one of them is not and one of them is, but this isn't like the right multiplication or something. This is
Slightly different, I think.
Oh, okay. But actually, so then I think I don't actually understand what this one is. Like, can you explain how you go from a map from O to Homs to an actual action on the Z thing?
Oh yes, this is easy. So if you have a map from, so if you start with a map from delta to Z of O, I'll drop the check to simplify. Then yes, if you have a map like that, you get an endomorphism of Z of O by just saying that. Yes, this is the same as Z of O of G convolved with delta. And then you have a map to Z of O of G convolved with Z of O of G. And then you can multiply and get back to Z of O of G. So as soon as you have, so this is as soon as you have a morphism from delta to Z of OG, you get an endomorphism of Z of OG. And okay, so from an algebra morphism from here to here, you get an action of this algebra on this object.
Thanks.
Okay, so the second step of this construction is to extend in a way this construction to the IU equivalent setting. So we have this category D IU and this subcategory of purpose sheaves. For this, they are associated with this T torsor FL tilde over FL. And we can play exactly the same game in this story. We have a subcategory, a SEA subcategory generated by objects corresponding to purpose sheaves associated to elements, simple purpose sheaves associated to elements of positive length. And then we have some monodromic quotient, which is defined just as before. And we have a quotient functor. And we have the same kind of arguments as before that give us some monoidal product on this category. Well, there is a slight subtlety that in this case, we do not have a unit object. And the product is only right exact, not exact, but that's a minor difference. And also, one can construct some monodromic version of Gates-Gouris functor. So instead of taking values in DII, now the functor takes values in DIU hat. And another important object that we need is this an object denoted by psi hat, which is the thing that you obtain from the unit object in the category D hat, and you take we take our averaging and then IU averaging. So this is the object in this completed category. This is the tilting object in this in the completed category corresponding to the finite flag variety associated to the longest element in the value. So this is something which is familiar from Zöger theory, and one can try to copy the construction, this construction of the functor, and for that, and this is what we're going to do, and on the coherent side, what we will get has to do with the universal centralizer. So over the adjoint quotient identified with T check mod W, we have this universal centralizer, which is a smooth group scheme. And we pull back this universal centralizer to the fiber product of two copies of T check over this adjoint quotient. And we look at representations of this group scheme, which are set theoretically supported on the base point. And this is what exactly the category that will describe this monodromic regular quotient. And so in this paper in preparation, we construct an equivalence of abelian categories relating this kind of regular quotient with representations of the universal centralizer. And okay, maybe I will not. So I will skip this construction. Well, the idea is just to copy this description of this equivalence to construct some functor and then prove that this functor indeed provides an equivalence of categories. And this equivalence is some kind of version of the equivalence that we were looking for over the regular locus, meaning that I have this multiplicative Schwenger resolution. I can look at the preimage of the regular part of G check in this Steinbeck variety, and it turns out that this pullback of the universal centralizer exactly controls equivalent coherent sheaves on this regular part. The category of equivalent coherent sheaves on this regular part is easily seen to be equivalent to representations of this group scheme, and the things which are set theoretically supported on base points correspond to coherent sheaves supported on the preimage of the unipotent part in G check. Okay, and so the main reason why we wanted to have such an equivalence is to get the following corollary, which gives some kind of Zögel type description of tilting perverse sheaves in this completion of the DF category. So maybe I'm really long, so I will not explain all the details, but we get a description of this category of tilting perverse sheaves in terms of certain Zögel type description, Zögel types subcategory of representations of some completion of our group scheme. So this involves the completion of this fiber product at the point 1,1, and we have a group scheme over this scheme, and we look at representations of this group scheme, and inside this category of representations we have certain objects, and we look at the subcategory generated under convolution, direct summands, and this gives some combinatorial model for the category of tilting perverse sheaves in this category D hat IU. And I can maybe very briefly so this is the second step of the project, and then there will be a third step which will. So in the second step, we have obtained some kind of Zögel type description of the constructible side, but we'll also have to have some similar picture on the coherent side. And so here we look at some, well, so this completion of this of the Steinbeck variety, which is just some fiber products of the Steinbeck variety with this completion of our scheme. And the idea, well, so what we will do in this project, in this third step, is describing this the category of equivalent coherent sheaves on this scheme as the homotopy category of certain subcategory of certain category D, which will have the same Zögel type description as before. And in this way, we will have a way to relate coherent sheaves on the Steinbeck variety to the constructible world. And well, and so this for this step we'll have to get back, in fact, to the additive version of all the geometry in order to use the localization theory developed by Bezukharnikov, Mekovich, and Ruminin. And well, we will use some version of this localization theory, which describe some Dirac category of equivalent coherent sheaves on the Steinbeck variety in terms, well, as a Dirac category of some category of Harish-Chandra bimodules. And then we will have some kind of Zögel functor describing these Harish-Chandra bimodules. Well, a certain category of Harish-Chandra bimodules in terms of representations of this this universal centralizer. And maybe I should stop here. And sorry, I was a bit quick about the end, but I'll be happy to answer any question.
Any questions for Simon? You mentioned you can deduce a proof of Finkelberg-Mekovich conjecture.
Yes. So this is some expected application of this construction. So the Finkelberg-Mekovich conjecture describes the principal block of representations of G-check in terms of the category of IU equivalent Pavlov sheaves on the Affine Grassmannian. And yeah, so the category of IU equivalent Pavlov sheaves well, embeds fully faithfully in the category of IU equivalent Pavlov sheaves on the Affine flag variety. And so essentially we expect to obtain this proof of this conjecture by identifying the image of this embedding and understanding what happens on the dual side. And on the dual side we expect to identify the image with this principal block here. Yes, so this is roughly the idea.
I see. Thank you.
So can you explain? So I think I was following up to the point where you got representations of this group scheme I, and how do you go from that to the Steinberg?
Well, so the point where we get from coherent sheaves, well, from Pavlov sheaves to representations, here is the end of the constructible side of the picture, and I'm saying that we have a similar kind of picture on the dual side. So the Dirac category of equivalent coherent sheaves on Steinbeck variety in here. So yeah, so if we want to pass to the additive version, and in the for the additive version we can use the localization theory which relates coherent sheaves in here in to some kind of some category of Harish-Chandra bimodules for the enveloping algebra. And in this category of Harish-Chandra bimodules, we have some objects which correspond to wall crossing functors. So these are some objects that appeared in my talk at the second conference of the special year. That so these objects already appeared in a different paper with Roman. So we have these kind of Harish-Chandra bimodules. And what we plan to prove is that, in fact, so this, well, that one can describe the Dirac category of Harish-Chandra bimodules has the homotopy category of this category of this subcategory. So inside here, we have some category that plays the same role as tilting perverse sheaves, meaning that we have a vanishing of higher x between these objects. So we have a functor from the homotopy category of a certain category, so something of this form, to the derived category of Harshana bimodules, hence to a certain category of sheaves on the Steinbeck variety. And so this reduces the question to describing this category of Harshana bimodules. And it turns out that this category of Harshana bimodules has again some description in terms of representations of the same group scheme.
Okay.
Any other questions? All right, if not, let's thank Simon again.